Thank you, Chair. Very good afternoon to all of you. It's a difficult session after lunch. You have been hearing about the corrosion, the basic chemistry, the physics, as well as the corrosion in refineries and other assets. I'll just take you through a journey wherein the corrosion in aircraft is a very, very important issue. And I'll just try to give you some of the strategies which are being utilized to mitigate these or to detect these the corrosion in the aircraft. So in the aircraft, there are large number of corrosions. So I have listed only the most important of them. For example, the stress corrosion, wherein the continuous exposure to the mechanical stress and corrosive environment takes place. Then the uniform corrosion, we also have the galvanic corrosion, because there are two dissimilar metals are joined at various places. The pitting corrosions, fritting corrosion I have not included, but that is also one of the most important aspect, which is one of the major issue, and the biological corrosion. Now, the corrosion has been a very serious issue in the aircraft industry. Even though we are talking about the composites they are used in the aircraft industry, as on today, the most advanced civilian aircraft or the military aircraft, they use to the tune of about 50% of the composite materials. But the remaining 50% is still made up of metals, depending upon the load-bearing capacity and things like that. So to protect the metals, there are a large number of surface modification technologies which have been discussed in detail in this workshop, as well as the paint related coatings which are applied on these metallic substrate, but still the corrosion remains a very serious issue which needs attention. So if you look at this Aloha airline flight Boeing 737, wherein there was a accident in 1988, wherein there is one casualty was there and a large number of passengers, there were a lot of injury was there. After this accident, a lot of research has been taken all over the world towards the corrosion prevention and the control programs by various aviation authorities such as FAA and ESA. In terms of the economic implications, it has been discussed in the morning also, that in US itself alone, the corrosion the cost of the loss in the revenue because of the corrosion is about $2.2 billion. And the corrosion of all the failures, it can be avionics or it could be other kind of failures, the corrosion amounts to about 25% of the failures which are occurring in the aircraft industry. Therefore, it is very, very important to address and to detect and to mitigate the corrosion in the aircraft industry. So towards that, the surface modification plays a very, very important role. I'm a coating person. So usually, for example, aluminum, which is most widely used material in the aircraft industry, because of its high mechanical strength but very low weight penalty, it is prone to corrosion. Now the surface is the corrosion, the aluminum surface is first anodized with either a chemical process, usually the chromic acid anodization, and then there is a primer layer is there, and then the top coat is a polyurethane coating. Now the efforts in building or in these technologies requires the involvement of large chemicals which are highly carcinogenic in nature. For example, the cadmium plating or the chrome plating, they are highly carcinogenic in nature. So as per the FAA or the other kind of pollution related guidelines, now the efforts are towards using the greener technologies, wherein we don't use any hexavalent chromium or the cadmium plating. So towards that, we have been working to develop a large number of coating processes as well as surface modification technologies at NAL. One of the technology which is developed and certified by Semilac is listed over here. Here we use the modified tartaric sulfuric acid anodization process in place of the conventional chromic acid anodization process, and this is it complies to the European regulations of REACH and ROHS environmental regulations, so it is fully green technology. Now, to address the corrosion in aircraft, generally in the morning also it was talked about the preventive maintenance. So there are two kind of maintenances taken place in the aircraft industry. First is the schedule based maintenance. So the aircraft is inspected at a regular interval, that the frequency of the interval depends upon the exposure of the aircraft to the either the marine environment or to other kind of areas which are very prone to the corrosion. And then the condition based maintenance, which is wherein the whole aircraft is monitored using the onboard sensors. The detection in the aircraft is basically done by the non-destructive techniques. So there are large number of NDT techniques, which some of them I have listed over here. Not all of them are listed over here because of the lack of time. We have liquid penetrant inspection. It's a very, very simple, facile technique. The X-ray or the radiography, the guided wave technology, the ultrasound inspection and thermographic imaging, and of course the eddy current. I'll just take two simple examples. For example, the first is the eddy current NDT. That is, we use a coil which generates the magnetic field, and then wherever there are corrosion products are there because of the discontinuous in the magnetic field lines, so we can map the whole aircraft by using this technology. But one of the greatest limitation of this eddy current NDT is that if the cracks are deep down on the surface of the aluminium or the metal, then it is very, very difficult to detect by using this technology. Same is the case with the X-ray NDT, which is also known as the radiography technique, even though it has been widely used in the aircraft industry. And here also the problem is that the minute cracks of to the tune of say width of few micron or depth of say few millimeter cannot be detected by using this particular technology. Now, of course, there have been a large number of efforts to use the reflection of light-based technologies such as D-side scanners. We call it that double pass retro reflection, as well as the edge of the light scanners which are being used widely by the US Air Force, the Canadian Armed Forces, as well as the Royal Air Force of UK to detect the corrosion for their fleet of, especially for the military aircraft. Now, as I mentioned that not a single technique can detect the corrosion in the full aircraft, because the aircraft is very complicated structure. So a combination of techniques are utilized to map the complete corrosion map of the aircraft. Some of the techniques are listed over here. For example, the guided waves, the eddy current, and then the ultrasound. You need to have a large number of techniques to map the corrosion map of the full aircraft. Now, coming to the advantages of these NDT techniques, these are very cost effective. These are well established for more than a century, and no design changes are required in the aircraft surfaces. And that becomes so it becomes very cost effective, but it requires highly skilled technician which can interpret and analyze the data. It's a time consuming, and the hidden corrosion, as I mentioned in one of my slides, is not possible by using these techniques. So recent years, the focus has been to use the onboard corrosion sensors. So here three kind of environments are there. For example, environmental sensor, So wherein we have the change of the relative humidity or the temperature or the concentration of the pollution or the chemical sensor, for example, pH, or the physical sensors. We use all these techniques to design the sensors for a given aircraft. So the various kind of onboard corrosion sensors are listed over here briefly. They are not the complete list because of the lack of time. I'm not going into the detail. So first is the corrosion coupons, which are placed on the different parts of the aircraft. Linear polarization resistance, acoustic emission, which is also part of the SHM of the aircraft, this thing, and optical fibers, wherein the changes in the material properties are investigated by using these optical fibers. So just to give you that electrochemical techniques, they are fast and facile technique for the direct detection of the corrosion, and the direct measurement of the corrosion changes is possible by using this technique. So the most two important techniques or the sensor which are based on this principle are the potentiodynamic polarization based sensors and the linear polarization resistant based sensors. This is the linear polarization resistance sensor, wherein it provides the real-time measurement of the electrochemical activity in the different part of the aircraft. So the corrosion sensors are fixed in the different location of the aircraft, and they are monitored by using the data acquisition system in the cockpit. And then this technology is being used in C-130 military cargo aircraft of the US Air Force, and it has been certified by FAA. And so this is a simple design that wherein we use the sensor is made of the same temper and the alloy. For example, if the fuselage is made up of say 2024, the sensor is also made up of 2024, and it is an interdigitate electrode which is embedded in the skin of the aircraft, and then the signal is directed to the data acquisition center. Now, one of the limitation of this technique is that it can give you only the uniform corrosion wherever the uniform corrosion is taking place in the aircraft. It does not give information regarding the localized corrosion in the aircraft. I'll just take another 1 minute. So these are the advantages of the onboard sensors. It reduces the aircraft downtime, and it has the wider reach to all areas of the aircraft. It's a real-time monitoring. Of course, one of the limitation of these onboard sensor is, of course, the weight penalty. But more than that, the installation cost is very, very high. And then the replacing or updating the sensor, if some sensor is not working, it becomes a very challenging. I have only one slide. So the recent advancement has been to use either the drones or the robots to map the full aircraft, and then to see that wherever there are some corrosion prone areas are there. And then it's a very simple technique, and it reduces the time. And as has been discussed in the morning also, the AI and ML also, they are going to take place. They are going to be the future of the corrosion sensor for the aircraft industry. As I mentioned, that the aircraft structure is a very, very complex structure consisting of a large number of materials. So it becomes very, very difficult to monitor and mitigate the corrosion in the aircraft. So this is the last slide. Despite all the measures taken for the corrosion protection, it remains a major concern for the structural integrity of the aircraft as well as the human life. The economics is, of course, it is there. So conventionally, as I mentioned, that we use the non-destructive techniques to detect the corrosion in the aircraft, but in futuristic approach will be that we use the combination of onboard sensors, automation such as the robots and the drones, as well as the artificial intelligence, along with the digital twin technology, to map the full aircraft so that we get the information about the corrosion areas in the given aircraft. Thank you very much for your kind attention.
Thank you. I'm really happy to see that the final slide talks about digital twin technology, integrates many things. I'm sure there are questions. So maybe one or two quick questions we will take now. Are there questions from the audience? Well, you made it so explicitly clear that
either
it
was
no
not.
need for any kind of good. Thank you very much.
Thank you very much.
Thank you.
Yeah.